Hello everybody. So in this video we're going to start the last chapter in this course, which is chapter number 9. And in this chapter we are going to deal with energy balance for reactive systems. So we already discussed in the previous chapter different cases for calculating the change in enthalpy and internal energy. We consider the case where the pressure is changing at constant temperature and phase, and the same for temperature, the same for phase. And we didn't cover the mixing of two liquids because it's not in the syllabus, but we have only one case left, which is the chemical reactions at constant temperature and pressure. So the chemical reaction is going to be a totally different thing. All the previous cases were physical systems. By physical systems, we mean that these are cases where we don't have any change in the chemical structure of the components that we have in the system. So it's either gas turning into liquid, liquid turning into gas, into solid, whatever the change that's taking place. It can include changing in temperature, changing in pressure, but still it has the same chemical structure. Now in the chemical reaction, it's a totally different story because we have a change in the chemical structure of the materials that are involved in the reaction. So to understand this, I'll take the first 2 or 3 times or videos as an introduction. We will cover the main concepts that we need to understand in order to go to the energy balance equation and see how can we calculate the delta H term for processes involving chemical reactions. So first, how do the reactions happen? First, the reaction happen in 2 main steps. This doesn't mean that this is what happens in reality, or this is the only 2, or these are the only 2 steps that take place. But these are the major steps. There are some reactions that can happen on 20, 30 steps, and this is not what we are interested in now. The details of the reaction and the steps of the reaction are studied in the chemical reaction engineering. It's a totally different course. But for now, we just want to focus on the main 2 basic steps, which are the breaking of bonds. For example, here we have 2 molecules or two atoms of oxygen held together with a covalent bond. So this is oxygen molecule. These are 2 hydrogen molecules. So in order to form new materials or new compounds, we have to break the currently available or compounds that we have. So once we break the bonds, the molecules or the atoms will rearrange themselves to form new bonds. So by doing this, you can see here that we have 2 molecules that are formed, which are water molecules. So this is the known reaction of hydrogen with oxygen to produce water. So this is these are the 2 main steps that are involved in the reactions. So breaking bonds is a step that requires energy, and the formation of new bonds is a process or a step that produces energy. And so we have 2 different types of energy absorbed to break the bonds and energy released after the formation of new bonds. And now we have two different cases, whether we have more energy required to break the bonds than the energy produced by the formation of new bonds, or the opposite. And this is what we call endothermic or exothermic reaction. So the exothermic reaction is an energy producing reaction, and this is because the energy produced by the formation of new bonds is more than the energy absorbed by or required to break the bonds, and the opposite. So this is a simple way of telling which is which reaction is endothermic and which is exothermic, based on the difference in the absorbed and the produced energies. So it's important for us as chemical engineers to understand this concept well, that it's not a simple thing. It's a very, very basic thing that to know that the reaction is endothermic or exothermic, and because there are a lot of things that will be depending on this. The design of the reactor and the design of the whole process might be affected by the type of reaction. There are some reactions that are highly endothermic, and this requires operating the reactor at very high temperature, and at the same time it requires heating the feed to very high temperatures before going into the reactor. So this includes many steps of heaters, maybe tube furnaces, and many other units that will provide energy to make the feed suitable for the reaction. On the other hand, if the reaction is highly exothermic, we need to make sure that the design is made to absorb all this energy that is produced from the reactor, which can be by using heat cooling jackets, can be by using tubes, cooling tubes, and cooling tubes inside the reactor. It can be by splitting the reactor into two and make an intermediate cooling in between. So there are many things that would be depending on the nature of the reaction. So this needs very good control on the system and very good knowledge of how much heat that is produced or absorbed in order to design the system accordingly. Yeah, because you don't want to run the reactor and then you suddenly realize that there is a lot of heat that is produced and it's leading to explosions or leading to melting of the reactor. It can lead to disasters. So this has to be well studied beforehand, and the heat that is needed to be absorbed or produced or given to the reactor must be well calculated and put into the design of the reactor. So this is why we care about this kind of things. طيب. Now let's talk about the delta H due to the chemical reaction. This is the main thing that we want to understand. So again, as I told you in the beginning, this is a special case compared to the previous cases. In all the previous cases, we had the same material in and out. Here we will have different scenario. For example, for this reaction that we have here, let's say we have A plus 2B goes to 3C plus D. This is the reaction that takes place in this reactor. And if let's say that the feed contains only reactants with stoichiometric ratios, I'm providing the reactants A and B with the ratios 1 mole A and 2 moles of B. And the reaction will go to completion. So all A and B are consumed in the reactor. So the product would be only C and D. And based on the stoichiometry of the reaction, we will have 3 moles of C and 1 mole of D. So in this case, if you think about this reactor the same way you're thinking about the evaporators or the heaters or the coolers that we used to see in chapter 8, it's not gonna work, because you have here materials that are not there, and here we have here materials that are not there. So when you calculate delta H, there is no enthalpy of C in and enthalpy of C out to get the difference. There is no enthalpy of A in and out to calculate the difference. So the materials that are here are different from the material that are on the other side of the reactor. In this case, we have to deal with it in a different way. So the components, since the components are different, we use a term that is only specific for the reactor, and this specific term is called the heat of reaction. And this is the first term that we will be depending on in order to calculate the enthalpy change in the reactor. So the heat of reaction, it is the enthalpy difference when the stoichiometric quantities of reactants at specific temperature and pressure, I say stoichiometric quantities, this is the same thing we said in the previous example, react completely and the products are at the same temperature and pressure. So we have the same components in the feed, the feed is at stoichiometric ratios, they are all consumed, and the product is only, the product stream contains only the reaction products. So for example, if I have calcium carbide plus water, they react to produce calcium hydroxide and acetylene, and this is what we call the heat of reaction. So this delta HR at this temperature and pressure, it's the enthalpy difference between the exit stream and the feed stream. Okay, so when we see the equation like this delta HR, it is the difference in, and this is the delta H for this system. Okay, so this is the delta H, this is the enthalpy difference between the products and the reactants. As we said, it's a different case. We don't have the same components in the feed and the product, so we have to deal with the heat of reaction. When we see this reaction, we understand that 1 mole of calcium carbide reacts with 2 mole of water to produce calcium hydroxide plus acetylene and 125.4 kilojoules of energy. So this is the meaning of the heat of reaction. And this delta H, it is based on this reaction that's written here, meaning that this delta H equals negative 125.4 kilojoule for 1 mole of calcium carbide reacting, for 2 moles of water reacting, for 1 mole of calcium hydroxide produced, and for 1 mole of acetylene produced. Keep in mind that these are all related. The reaction combines all these together, so it's not something that we can split. I cannot say that this is the enthalpy for only 1 mole of calcium carbide without reacting with water. This will not happen. So this number is translated as we see here. It is for 1 mole of calcium carbide, for 2 moles of water, for 1 mole of calcium hydroxide, and for 1 mole of acetylene. So this is how we define the heat of reaction. We also, this is important that we give the symbol negative here as we do it for work and for Q and for heat. That this is negative if it is produced, it's positive if it's absorbed. So if the reaction is exothermic, it is it's going to be a negative sign. If it is endothermic, it's going to be positive sign. So as we see here, this seems like the specific enthalpy before. This is per unit material, or per unit mole of the materials. So if you want to, if I have, let's say 100 moles, if I have 1000 moles of calcium carbide reacting with 2000 moles of water, how much energy? Of course, the energy is going to be multiplied by the number of moles. So if we want to get the total energy generated, or the rate of energy generated, then it's going to be multiplied by the number of moles. So delta H equals, if I have 100 moles, let's say, of calcium carbide, so it's 100 moles multiplied by this negative 125.4 kilojoules per 1 mole of calcium carbide. This gives us the total energy produced from the reaction. If it can be applied for the rates, and if I say that the heat generated due to consumption of 50 moles of water per second, so I know that this is 50 moles per second, and this is the energy per 2 moles of water. This gives us the total energy in kilojoules per second, or the rate of energy production. So in general, we can write the energy, the enthalpy change due to the reaction as the heat of reaction divided by the stoichiometric coefficient multiplied by N final minus N initial, which we can call the NIR, which is number of moles of species I reacting. So again, this is the heat of reaction divided by the stoichiometric coefficient multiplied by this. And if you see this number, this is the stoichiometric coefficient of water. If you go to the previous, it should be -2, but it's going to be, as we'll see, it's going to be the same. So here it is -2, or this should be -1, and at the same time we have this should be -100, because this is the number of moles final minus initial. So if I have 100 moles, they are all consumed, so the final is 0 and the initial is 100, so it's 0 minus 100 divided by -1. So it's the same. And the same here, it's 50, it should be -50 because it's consumed, so it's the final minus initial divided by the stoichiometric coefficient. Or we can just write it in this form, which is easier. This is the number of moles reacted, either consumed or produced, the absolute value divided by the absolute value of the stoichiometric coefficient. So in this case, this equation can be used to calculate the total energy produced, or the total rate of energy produced if it is per unit time. So this is simply how we can calculate the total rate. There is a simpler way to do this by combining what we did before, or what we know from before. If you look at these two terms, this is what we used to define as the extent of reaction. So if you recall the definition of the extent of reaction, it will be NIR over the absolute value of the stoichiometric coefficient. So if you combine the previous example, or the previous shape, with the current shape, you can see that it is extent of reaction multiplied by the heat of reaction. This is the total heat of reaction. And also for continuous reactor, this is the derivation. It's a little longer, but at the end of the day, I don't want to waste your time in this, but at the end of the day, this is what I want to reach, that the difference in enthalpy, or the delta H, it's going to the extent equal to the extent of reaction multiplied by the heat of reaction. So in short, just to compare what we used to see before to what we see here, that this is the specific enthalpy change in case of physical systems. This is the delta HR, which is heat of reaction for chemical systems. And to get the total enthalpy change, we used to multiply this by N or by M, according to what is this, if it's per mole or per mass, to get the total energy. And the same here, you multiply delta HR by the extent of reaction. So it's the same thing, almost the same thing. And we will see at the end of this chapter that we will do the two steps in the same calculation. So you can add a term in of this form to a term with this form. So it is almost the same thing. So this applies to rates. This applies to just number of moles for the extent of reaction, or for I mean for continuous, or for batch, or for number of moles, or for rates. So this is all what we want to say here. We will continue next time to talk about this in more details and discuss more things. So I'll see you next time, inshallah. Goodbye.